Hey, it's Monday. No, yeah, Monday, February 6th. It's a snow day, but we should still get something accomplished here. Essentially, what I want to say is multiply by t. And I could cut this video off right now, and that would be all I really need to get out of section 3.4. But let's justify the multiplying by t a couple of different ways. Okay. Anyway, we're dealing with second order differential equations, such as this one here. We want to find the general solution. As in any second order linear homogeneous with constant coefficients, we're assuming that y equals e to the rt for some r. You plug that in, you plug in r e to the rt for y prime and r squared e to the rt for y double prime, and you get this second, no, what is this called? It's a quadratic equation, and you solve for r, and you get r equals -1 or r equals -1, which only gives us one solution, r equals -1. So y equals c1 e to the minus t plus something, and I need something else to make the general solution here, right? Last week, we used Abel's theorem and found the other one in the following way. We have this differential equation. Abel's theorem says that the Wronskian of two solutions is going to be some constant times e to the negative integral of p of t dt, and in this case, p is 2. So we get the integral of that. So anyway, and c is e to the negative 2t. So setting up the known solution, e to the minus t, and the unknown solution, y2, taking the Wronskian of those, we know that it has to be equal to this. And we're choosing c equals 1 here. I only need one solution. I don't need infinitely many, so I'm just picking c equals 1 for simplicity's sake. Taking this, what is this called, a determinant, I get the following on the left, and that's going to be equal to this. This is now a first order linear equation in y2. So dividing by e to the negative t, or multiplying by e to the t, whichever way you want to think of that, I get this equation. The integrating factor is e to the t. So anyway, you multiply by e to the t. The left-hand side is the derivative of y times e to the t. The right-hand side is just 1. So when you integrate both sides, you get y times e to the t, the integral of 1. Anyway, notice that integral of 1 just becomes a t. Well, it's t plus a constant anyway. And for simplicity, I'm taking the constant equal to 0 because I only need one solution, and I end up with my solution, y2, is t e to the minus t, which notice is just t times the one you had before. So you have the e to the minus t, and you have t to the minus t. And you have your solutions, and you're good. So now let's do another problem. That's the way we did it before. Let's do another problem by the method the book uses. So here we go. This one is y double prime plus 4y prime plus 4y equals 0. Again, assuming y equals e to the rt is a solution, we get a quadratic equation that looks like this, and it tells us this time that r is equal to -2. So my solution, y1, is e to the negative 2t. I need a second solution in order to find all the solutions to this differential equation. So this is a method called reduction of order. And essentially, we know that multiplying this solution by any constant would give us another solution. And so someone, somewhere along the way, well, of course, people tried all kinds of different things, and a lot of them didn't work, so we don't hear about them. What we do hear about are the things that worked. And so someone said, hey, what if rather than multiplying a constant, what if I multiply by a function and see if I can get this whole thing, this function u times e to the negative 2t, that whole thing to be a solution. Now, first of all, I want to point out that this does not, this is a pretty broad situation. You might think, oh, but why, not all functions have e to the minus 2t as a factor. You can have all kinds of things, but this could be any function you want. This could be sine of t, because you could say, well, u of t is sine of t divided by e to the negative 2t, and e to the negative 2t's cancel out. So any function you want, you can get from this form. So this is why it works is seemingly baffling, but anyway, it works. So the thing is, I want to find u so that this product is a solution to the differential equation. Taking the derivative using the product rule, I get this, and then taking the second derivative using the product rule twice, because you got to do it on this and you got to do it on that, you get this whole thing, which is equal to this whole thing. There's some stuff that combines here because the middle terms, this one here and that one there, combined to be this minus 4 u prime e to the minus 2t. Okay. I'm going kind of fast here. You can work through the algebra yourself here. It works just fine. So now plugging stuff in for y, y prime, and y double prime, we get, well, there's y double prime plus 4y prime plus 4y is supposed to equal 0. So let's see, gathering some like terms, stuff with y double primes in it. There's only this one right here. It's there. Stuff with y primes. There's one y prime right there. Sorry, u primes, u double primes, and u prime, u prime. Anyway, so we get to there. That's a 0, and then all the stuff that have just u's. So there's the 4 there. There's that one there, and there's this one here. Those all come up to here. Hey, look at that. Those add up to be 0. Oh, look at that. Those add up to be 0. Beautiful. So you end up with just this equals 0, which tells you that u prime has to equal 0, which means if you integrate, then, so u double prime is 0, so u prime is a constant, and u is some constant times t plus k. We are not looking for all the possible u's, we just need one. So take k equals 0, k equals 1, and there you go. You've got this t times e to the minus 2t to go along with the e to the minus 2t that you started with. So multiply by t. Now, apparently I had an initial condition stated up here, and I haven't gone back and said, let me solve for that, C1 and C2, but you could do that. One of the things I want to point out is that the derivation they do in the book is for a general second order linear differential equation, homogeneous. Not necessarily constant coefficients. They have a p of t and a q of t here. And they show that no matter what p and q are during this, if you've got one solution already, they do this reduction of order thing, and they show that this one right here turns into 0. Not necessarily this one. But that being said, they've got a u double prime and a u prime times something equals 0, and they say, well, but this is a first order linear equation in u prime. So normally we have y and y prime, now we got u prime and u double prime, so it is still first order, and we can use the methods of first order differential equations, or linear ones, to figure out what u prime is, and then just integrate that to get u. Okay. In the event that we're dealing with these that we're doing now, where you've got constant coefficients and you already know that the quadratic equation that you get out of this has only a single real solution, then this and that will both be 0. This is a special case if this one turns into 0. And in that case, you just get that u double prime is a 0, and so u's got to be a constant times t, so just take t. Anyway, multiply by t, that's what we do. So here's the general solution, that if you've got a second order linear homogeneous constant coefficients, and the coefficients are in this relationship that this is 2 alpha where that's alpha squared, then this factors into r plus alpha and r plus alpha. And so you have y equals e to the minus alpha t. Notice that Abel says that the integrating, no, what is this? The Wronskian should be some constant times e to the negative integral of p of t dt, which is just this e to the minus 2 alpha t, which is where I'm using Abel's theorem here to find a second solution. I'm claiming that it's just going to be t times that. This is the general proof that just multiplying by t works in this case. Okay. So you can follow it through. It's the same thing we did on the last one. It's you get this, take the Wronskian on the sides, excited equal to that. Abel says it's equal to, and you get this first order linear equation in y2, and you get the integrating factor, and you solve it all out, and oh, look at that, you get t e to the minus alpha t. So anyway. Oh, looks like I do come back to it here. With these solutions, with these equations where you have that quadratic which factors into 2 of the same factors, then you're going to have an exponential and a t times an exponential as your 2 independent solutions. And this is just solving for T1 and T2. Anyway, I think that's probably enough for today. You should try some of these. We'll come back on Tuesday and answer some questions and maybe talk a little bit more about this section 3.4, but then move on. It's not really rocket science here. Actually, maybe it is.